So I want to go over the last one on the quiz first, because that's the one you're actually going to be doing in lab. So some of you will have a pre-lab view on that next week. And that's cyclohexadiene with N-phenylmalayamide. And you're right, the N-phenylmalayamide like this, so that the carbonyl groups and secondary orbital overlap back here. I'm just going to write this PA, so I don't get active radium there. This is a little different from the ones you have been working with, because this is actually a 6-pi orbital system. Because you've got the 2 carbon-oxygen double bond and the carbon-carbon double bond. So in this case, what we want to be looking at is the LUMO, which is pi 4 star for this orbital. As a 6-pi orbital system, the energy diagram looks like this. And this is a normal Diels Alder reaction because we have 2 electron withdrawing groups on the dienophile. We don't really have anything particularly electron donating or withdrawing here, but these 2 CH2 groups are kind of electron donating by hyperconjugation. This reaction is only possible because the Diels Alder reaction is disrotatory, because you couldn't do a conrotatory motion here without breaking that ring. So to look at this in orbitals, we want the usual pi 2, which is the HOMO. For the diene, and for the dienophile, we want that 6-pi orbital system. So there's going to be 3 nodes. 4 pi 4 star. And we're going to have secondary orbital overlap here and here. From the 2 carbonyls going into the back end. And then we're also forming new bonds between this one and that. And we're forming a new bond between this one and that. It's going to be a disrotatory closure, which means these 2 hydrogens are going to end up going down, and the bridge is going to go up, and the endo positions, which is where the carbonyl groups are going to end up going down. So the product will be a bridge bicyclic structure, which has the double bond on the bottom part and the single bond on the top part. 2 hydrogens will be in the exo position, and then my ring will be down like this. So I've actually got this 5-membered ring of nitrogen on the same side of that kind of cyclohexene as where the pi bond is. And the 2 hydrogens on the same side. And this is where the terms endo and exo actually come from. It comes from bicyclic structures like this, where the exo positions are the ones that are pointing away from the kind of cyclohexene, and the endo positions are the ones that are tucked under where the cyclohexene is. So the difference between this and the ones you've been working with is it's a 6-pi orbital system rather than a 2 or 4-pi orbital system. The first one was a 4-pi orbital system. So the endo rule is followed, and that's what causes the relative positioning of this nitrogen-containing ring and the pi bond. So there was no regiochemistry to worry about here because both molecules were symmetrical. And there was no stereochemistry to worry about on the dienophile because it was obviously tied into a grid. So the first one has an NH2 group ways to react. And then we had a cyanide group and an methyl group that were trans. So we can write the mechanism if we want with the transition state. So we know that these are going to stay trans because there's a partial pi bond here. So we have retention of stereochemistry at the nanophile. But the transition state doesn't really tell us anything about the stereochemistry. It just shows the relative positioning of the nitrile and the amine. It doesn't tell us anything about the relative positioning of the CH3 in the amine. The resonance structures that you can draw for this look like this. Where you get a negative charge of nitrogen. That leaves you with a positive charge over on the methyl group by just moving this over here like that. And the resonance structure that you can draw for this, there's a double bond of nitrogen here. And a negative charge on that end by moving this pair of electrons like that. So regiochemistry, the negative charge on this end and the positive charge on that end want to get together, which means your cyanide group and your NH2 are going to be in a 1-2 relationship rather than 1-4, as I showed here.
Wait, it would be 1-3 if it wasn't. I don't think it was 1-4, right?
1-2 rather than 1-3.
Okay.
Yeah, 1-4 is not possible for this system. Diene HOMO is still pi 2. Or 4 pi orbital system. This is now also a 4 pi orbital system. LUMO, pi 3 star. So we're going to get a new bond here and a new bond here, and then we've got our secondary orbital overlap there. In the back end of the pi system and the compartment of the nitrile. This rotatory motion is going to move the two outer substituents, the NH2 and CH3, down. Those are the two that are in the E position. And this rotatory motion, or I'm sorry, the diene is kind of folding over. When we call that endo substituents go down and the substituents go up. So when we're done, our nitrile down, we want our NH2 also down. We want our methyl group up. Outer substituents, the NH2 group and the CH3 are both going down from the disrotatory motion. The nitrile is going down because it's in the endo position for secondary orbital overlap, and the methyl is going up because we have trans dienophile trans alkene to start with, and we've got that 1-2 orientation because of the resonance structures. If you wanted to draw the mechanism from here, right, you would show this pair of electrons going back in to form the triple bond. This would come over here. Push the pair of electrons down onto the nitrogen to get the final ring. And then the last one was the inverse-electron-demand. We've got 3 electron withdrawing groups on the diene, 2 trifluoromethyl groups that are electron withdrawing inductively, and a nitro group which is electron withdrawing by resonance. Again, the first step is to rotate it into the S-cis conformer. the CF3 groups is inside, the other one is out. Here. So we can write a resonance structure for that. Where we pull this pair of electrons out to the nitrogen. And the positives are here. And then we've got our methoxy group. Over here. We're going to want that methoxy group to be in the endo position so that the lone pair on the oxygen can interact by secondary overlap with this material. So we can move that methoxy group. And we're also going to write a resonance structure that puts a negative charge out on the end and a double bond to the oxygen. That's going to cause the preferred arrangement to be the 1,4 in this case also rather than the 1,3. There's no stereochemistry to worry about on the dienophile because it's heavy. And then we're going to be moving this pair of electrons back on nitrogen to form that NO double bond. Push this piece over like that. We want to draw the mechanism from the resonance structures. This is in the endo position, so it's going to go down. It's going to be on the opposite side of this. This is now inner. Up. Outer here goes down. So the product will highlight the NO2 group here. That's a sp2 planar carbon, so we don't have to worry about that. This CF3 ends up going up. There's some trans to the methoxy group. This CF3 group ends up going down. So we've got a trans arrangement between the two CF3 groups. One was in the inner and one was on the outer. Their retention of stereochemistry from the stereochemical motion. And if you wanted to show the orbitals, same profile of the system that we're working with here. And we've got our pneumotype star. We've got one there, and this pair of electrons going in the end through secondary overlap. Stabilize the transition state once those exact things down. So you'll see as you do the dissociatory motion, the CF3 group goes up, this one goes down, and the nitrogen goes up. You get kind of stereochemistry. So there's a lot going on in the Diels Alder reaction. It's a complicated reaction. Hopefully we're able to at least address most of those